Good morning, everybody. Now that we've had an introduction to motion in two dimensions, we're going to start looking at how we describe different motions in two dimensions and how to solve problems. So projectile motion is what we're going to be working with the next couple of weeks or so. So we will start today, if you'll turn to the second page of your notes, with half parabola projectile motion, baby steps, okay? This is the simplest, so we're going to start with this. Now, let's suppose, and we're going to be doing some diagramming. In fact, I'm using red, blue, and green, and I'm going to make a little key right up here at the top. I'm going to use blue for horizontal, and I'm going to use green for vertical motion, and I'm going to use red for anything else like resultants, the combination of the two, okay? Now, let's suppose that we are standing on top of the North Campus gym, because that's a nice high place from which to project objects. So what we're going to do is we're going to project a ball horizontally off the building. That means we're going to throw it, and when it's released, when we release it, it has a horizontal velocity only. No up, no down, simply straight out. Okay? So here's the ball. And it's going to have an initial horizontal velocity, V sub I H, initial horizontal velocity, okay? Now when we release it, it will follow a path that looks something like this, okay? And we're going to look at several points along this path. So let's mark the points where we're going to look. We'll look at this one maybe, and one right here, one right here. We'll kind of evenly space them a little bit, okay? Oh, that worked out nice, okay? So let's look at those points for a minute and talk about the horizontal motion. As the ball, once the ball is released, that's when it's become a projectile. Now, when it's in your hand, it's not a projectile yet. Remember, projectiles, the only force acting on them is gravity, so they are in free fall. So it's not a projectile until it leaves the device that's projecting it or your hand. So once it is a projectile, then there is no more horizontal force acting on the ball to affect its horizontal motion. Remember, perpendicular vectors are independent, so the gravity cannot affect the horizontal motion. So the horizontal velocity is going to stay constant for the entire trip. So we're going to draw at each of these points the horizontal velocity vector the same size. It doesn't change. So right when it hits the ground, the final horizontal velocity is going to be the same value as the initial horizontal velocity, okay? All right, now, because there is no force acting to change the horizontal motion, that means the horizontal acceleration is going to be 0. Now, this is important. In a problem, they're never going to tell you this. This is one of the things they'll never tell you. So this is what I call an inferred piece of information that you will need to know based on understanding the motion of a projectile, okay? So that's one of the inferred pieces of information that we're going to need to remember, okay? Now, as the object moves horizontally, it will travel a distance horizontally that we're going to call d sub h, the horizontal distance traveled by the object. And this distance actually has its own name. It's actually called the range. Have you ever heard of them firing missiles downrange? Well, there you go. That's the horizontal distance the missile travels. Next, let's talk about the time it takes to travel this distance at this speed with no acceleration. We'll call it a time t sub h, the horizontal time. But strangely enough, there is a common name used for the time for the motion of a projectile, the time that it's in the air. I don't know if y'all remember this term, but I think it's used in football quite often, so you football players probably know better than me about that. But it's actually called the hang time, the time that it's in the air, okay? In other words, the time it's hanging around up there. Now, let's describe this horizontal motion two ways. We're going to describe it first mathematically. So here's the mathematical description for the horizontal motion. All right? It is moving with an initial velocity and goes through no acceleration. Now, that makes this a case 2 for the general equation. So let's look at it. If we write the general equation out, we get the horizontal distance traveled equals V sub OH or V sub I, well, I or O, whichever one you want to use. Stupid me, I keep kind of interchanging them, I'm sorry. In any case, V sub OHT plus 1/2 AH T squared. So I've got it modified for horizontals only. You cannot stick anything vertical in here when you're talking about horizontals because verticals have nothing to do with the horizontal motion, okay? So now, we've got this modified for horizontal side only. So we're going to look and see, oh yeah, but the horizontal acceleration is 0. And 1/2 times 0 times t squared is just going to be 0. So this drops out, as it will do in any case 2 situation, and we're left with this right here, a description of the horizontal motion of any projectile, which, if you'll remember, this is the definition for constant velocity, okay? So, the horizontal motion is constant velocity. Now, let's take this and describe it in English, verbally. So, what do we know the projectile does? Well, remember, it's a case 2. So, we can say the projectile has an initial velocity which stays constant. No acceleration, right? Now that wasn't too bad, is it? The horizontal motion is always simple. In fact, I'm going to tell you right now, and you keep this in the back of your mind, any projectile, I don't care if it travels a half parabola trajectory, I don't care if it's a full symmetrical parabola or a non-symmetrical parabola, the horizontal motion of any projectile is always this. Doesn't matter what the shape of the parabola is. It's always constant velocity because, again, there is no horizontal force acting on the projectile, and the vertical forces, gravity, has nothing to do, it won't affect it. So it keeps traveling at constant velocity in the horizontal plane. Okay? Now, let's take a look at the vertical motion, and I'm going to use green for that. It helps to keep things visually separated, all right? So green for vertical. Let's talk about what happens the instant we release the ball. We give the ball an initial horizontal velocity. That means when we release it, its initial vertical velocity is 0. In other words, it has to start falling due to gravity, okay? So it starts with an initial velocity of 0. Now, for any projectile launched horizontally, this is inferred. They're never going to say, oh, by the way, don't forget the initial vertical velocity is 0. That's not happening. They're going to expect you to understand from the situation when it is projected horizontally, it must start from rest in order to accelerate down. And speaking of acceleration, the acceleration in the vertical plane, since the only vertical force acting on it is gravity, the acceleration will be that due to gravity, okay? Which is going to be 9.8 meters per second squared. All right? And is anybody going to tell you that it's going to have that acceleration? Absolutely not. So here's the third piece of information that's inferred in a problem. They're not going to tell you because they're going to expect you to know that only gravity is acting on the ball, and that's a vertical force, so it affects the vertical motion with this acceleration. Nobody's going to tell you that. They're going to expect you to know that. So these three items are extremely important when it comes to solving the problems. You need to know this. Okay? There's sometimes in life when we just have to memorize stuff. We just have to know it. So make sure you get this down now. If you wait till later to try to get this down in your head, you're going to have a lot of trouble. You're going to struggle. Okay? Now, just like we did before, let's describe the vertical. Oh, wait, I'm not finished laying it out. I'm sorry. All right, so we've talked about the initial vertical velocity and we've talked about the vertical acceleration. Let's look at what happens to the vertical motion as the ball falls. Okay, so right here, it starts from rest and it's going to start accelerating down. That means the velocity is going to increase in magnitude as it travels downward. All right, so here's what happens to the velocity. It gets bigger and bigger, just like that. Okay, it's going to increase by increments of 9.8 every second. Now, this means that the velocity, and I think you've seen this on some of the videos that you've watched, this is why the resultant velocity changes direction. One component of the resultant velocity stays constant. The other gets longer. So that's going to change the magnitude and the direction of the resultant velocity. In fact, we say it stays tangent. All right, if we draw the resultant, and we can do that by placing these two tip to tail. Just think of sliding it over. So the resultant velocity is going to get bigger and bigger and be tangent. You can draw those if you want, but it's kind of making the picture messy, so I'm not going to continue. Down here, if you bring this over and put them tip to tail, the resultant velocity would go like this, okay? Now, let's talk about how far the ball travels vertically. It starts up here and it ends down here on the ground. So it's going to travel a vertical distance. Now, believe it or not, there's a name for the vertical distance traveled. And I think you can think of what it is if you just use a little common sense. It's called height. How about that? That's a word we know already, height, okay? All right, now, let's take a look real quickly at, the hang time. That's the other thing I was thinking of. The hang time. The vertical motion will take place in a time we'll call t sub v. But guess what? It's the same time as the horizontal motion. Both motions are taking place at the same time. That is the only variable that is the same for both motions, okay? In fact, we say that both motions take place, I'm going to use red for this, concurrently. Both motions are concurrent. Concurrent is a term that means with time. So concurrent means they take place at the same time. Okay? All right. Now, let's describe the vertical motion. Now that we've got D and V and A and a T, let's look at the mathematical description of the motion. And then once again, we're going to look at the general equation, but we're going to modify it for verticals. Okay? Now, this time, we know that the vertical initial velocity starts with 0. So 0 times t is 0, that drops out, and we're left with the vertical displacement equals 1/2 a/t squared. In this case, let's make the a g for the acceleration due to gravity. And that's how we describe the vertical motion of a projectile mathematically. Okay, at least a half parabola anyway. Now let's do it in English. Okay, in English, we can see that the projectile starts from rest. We saw it right up here, so let's say that. The projectile starts from rest, and then what does it do? It accelerates uniformly downward. So then accelerates uniformly down, right? Until, of course, it hits something. It can't fall forever. Eventually, it has to hit something. Okay, so we've got two independent motions taking place at the same time or concurrently. We've got the horizontal motion that we've seen. We've got the vertical motion that we've seen, okay? Now, let's take a look at how we would look at this same motion graphically. It's important to understand what the graphs would look like for an object traveling as a projectile. Now, since the vertical and horizontal motions are independent of each other, okay, remember they are independent of each other, we must look at the object as having two distinct motions, one in the vertical plane, one in the horizontal plane. So that means we have to look at the graphs the same way. We have to separate the motions out because they are independent. So let's start with the horizontal motion. This one's going to be easy. Let's look at the position of the object with respect to time as it travels. Okay, so this is going to be the hang time right here. The object, as we know, starts at an initial position horizontally right here. And whenever we start measuring distance, usually what's the first measurement? It's 0. Okay, so it starts at this position, and then notice as we travel downrange, the position gets larger and larger and larger and larger because we're traveling more and more distance. So distance being up the x-axis, let's put our final position, let's put DH right there. And when have we reached DH? Oh, at the hang time. So now how do we connect these two to show that we started at 0 position and ended up at DH in this hang time, but we did it at constant velocity? Oh, we show a straight line, just like that. So this describes the horizontal displacement of the object in the hang time. Now, real quickly, let's take a look at the velocities. All right, we've got velocities forward and velocities in the reverse direction, but I think you know we won't need that because it never went backward, did it? It always stayed in the same direction. So let's think, what initial velocity at 0 seconds, and let me put the hang time symbol right here, okay. What initial velocity did we have? Well, when it left our hand, it was traveling with a velocity we called VIH, right? So let's mark what that is. Somewhere up here is the value for VIH. And what happened to that velocity as it traveled along the range? Nothing. It stayed constant, didn't it? So that means at the hang time, it's still the same value, and we connect those with a zero slope straight line, okay? All right, so here the slope represents the velocity, and it shows that we're having constant velocity. Here, the slope is the acceleration, and this shows we have no acceleration. So how do we plot that on an acceleration time graph? Oh, that's easy too. If you have no acceleration, you're on the x-axis where it's 0, isn't it? 0 acceleration. There we go. So those three graphs describe the horizontal motion of a projectile. Now, real quickly, let's take a look at the vertical motion. All right, let's start with position. And I'm going to use a Y for vertical position. Does that make sense to you guys? I hope so. And there's the hang time. Now, let's look back at our picture a moment. Where did the object start? When we measure vertically, we typically take the ground to be 0 height. That just makes common sense, doesn't it? The ball started way up here at dV, not down on the ground at 0. So that means on our graph, we need to start up here at dV at 0 seconds. But when we get to the hang time, we're on the ground at 0 meters. So we make a dot there. But how are we going to connect these two to show that we accelerated? That means the slope can't be constant like it was here. We have to show an increasing slope to show increasing velocity as it falls. So that means we have to curve it like this so that it gets steeper and steeper. Okay? And look, that's a half parabola, isn't it? Okay. So this describes the vertical position of the ball at each point in time. The slope is the vertical velocity, and it's showing that it's increasing downward. We'll take the negative direction to be down and the positive direction to be up, okay? All right, now let's take another look at the velocities. Positive velocity, negative velocity. Here's the hang time. What is happening to the velocity? Well, as you know, it started from rest. So at 0 seconds, we have 0 velocity. And then it increased downward, didn't it? So at the hang time, it had some final vertical velocity. Don't know what it is, but it had it. It wasn't at rest again. Okay, when it struck the ground, it was moving with some final velocity. Now, after it strikes the ground, that's a whole different motion. That's not part of the projectile motion anymore, because when it strikes the ground exerts an upward force on it to slow it to a stop. We don't care about that. That's not part of the projectile motion, because that means the ball is no longer in free fall if another force other than gravity acts on it. So, the projectile motion stops when it strikes the ground. So, to show that the velocity uniformly increased in the downward direction, we draw a straight line connecting the two. Okay? Now remember, this is down and this is up. So, we have a slope that shows an increasing velocity in the downward direction. Okay? All right, now let's take a look at the acceleration in the vertical plane. All you have to do is go back up and look. Look right here. We said what it was, didn't we? It's right here. 9.8 meters per second squared, but down. So let's take a look at where we would put that. Okay, here's the down directions. Here's the up directions. So down, and I'm just going to label it as G. We don't really need any numbers right now. And it's uniform. It's always the same increment of 9.8. There we go. So for the entire trip, you had 0 horizontal acceleration, but you had G pointed down vertical acceleration. Okay? There we go. All right, if you'll change your paper, we're going to take a look real fast at this last one. Okay? We're going to actually do an example for a half parabola problem. I think you guys will like this. It's not too bad. First, to help you separate the two motions, because remember, you cannot use vertical information to find horizontal information or vice versa, because the two motions are independent. The only thing that you can use between the two is time, because both motions take place in the same time. Now, in order to help us solve the problem, I'm going to show you how to create a DVAT chart. One side's going to be horizontal, one side's going to be vertical, and you have a line for displacement, initial velocity, acceleration, and time. DVAT. See? DVAT chart. Now, before you start a problem, remember, if it's a half parabola, there are certain things you know that are always going to be true, and we can go ahead and put them on the chart. So I'm going to do that right now. On the vertical side, we know it starts from rest and accelerates down due to gravity. Okay? Those two things are inferred about the vertical motion. On the horizontal side, we have one inferred piece of information, and that's the horizontal acceleration. No horizontal forces acting on the ball, no acceleration. Okay? Now, let's read the problem. Notice all this missing stuff. Let's see what we can put in. A stone is thrown horizontally at 15 meters per second from the top of a 44-meter high cliff. Now, this word right here, this phrase is what gives you the information that it is a half parabola. It is projected, thrown horizontally. So that means it is a half parabola problem. We want to find two things. How long does it take the stone to reach the ground, and how far from the base of the cliff did the stone land? Now, let's follow our process. Identify any numerical information given. Well, look, it says it's thrown horizontally at 15 meters per second. So this is the horizontal initial velocity. So we put it right here. Then, it says it's thrown from the top of a 44-meter high cliff. Well, height, that means this is the vertical displacement. Height is vertical, so 44 meters. I don't see any other numbers, and we already have our inferred information in there. So let's see what we're trying to find. How long it takes, well, that's the time, right? And how far from the base of the cliff did the stone land? Well, if you're looking at the base and you're going outward, that would be the horizontal distance, wouldn't it? So we want to find this and the time. Now, how are we going to do that? Well, look at the chart. Now, in algebra, they gave you a good piece of information on how to solve problems, and that is start where you have the most information. Notice, 2 knowns, 2 unknowns. 3 knowns, 1 unknown. Here's where we want to start because here's where we have the most information. Now, what formula are we going to use? Well, look right here. D, V sub O, A, T. There's only one formula that contains all 4, guys, the general equation. So to get the time on part A, I am going to chuck in my vertical information into the general equation. So I'm going to write it modified for the vertical information. Now remember, this piece goes out. We're left with this. So now we get, if we want to do some algebra to solve for t, let's get rid of the half by saying 2 times both sides. Let's get rid of the g by dividing it over, since we're multiplying it on the t. And finally, to get rid of the square on the t, we're going to take the square root of both sides. So we get 2dv over g. And you see how I switched it right here so that I'd have my t on the other side? Yeah, don't switch. Don't try to move your t over right here, or you're going to really screw up. A lot of you did that on the linear kinematics test. You were trying to solve for the a, and you thought you could just bring it over here. No, you cannot. That is incorrect algebra. You have to go by reverse order of operations. So you cannot just move it over. Wait, leave it where it is if it's on the numerator on the right side. Just leave it there until you get towards the end. Then when it's by itself and you want to switch it, certainly you can do that then. You can switch both sides. So here we go. We're going to say t equals the square root of 2 times 44 meters over 9.8 meters per second squared. Notice you're going to get, when you flip the units to multiply, you're going to get these two canceled, and you're going to be left with second squared in the top. And of course, the square root of second squared is second, so you're going to end up with the right units. So we get 88 divided by 9.8, and we're going to take the square root of that, which I believe is about 3 seconds, and you can double check me on that. But now we know the time that it took this projectile to fall and hit the ground. And guess what? That's the same time it has to travel outward at 15 meters per second. Okay? Basically, vertical motion controls the hang time. Because once an object falls and hits the ground, all the motion stops. Both halves, the vertical and the horizontal, they both stop. So basically, vertical motion controls the time. And in that time, it will also travel outward. So now we can have enough information, 3 knowns, 1 unknown. We have enough to find the second part, the horizontal distance. So we're going to write out the general equation again. And we know this part drops out. We're left with constant velocity. So we get dh equals 15 meters per second